In this video, we discuss learning outcome number 2 of lesson 8.1, which is about significance level of hypothesis tests in type 1 and type 2 error. We're continuing what we did in lesson 8.1 learning outcome number 1. There we were defining and interpreting essential terms related to hypothesis testing as well, but now we're going to focus on significance and type 1 and type 2 error. My goal for you is that by the end of this video, you'll be able to identify the type 1 and type 2 error for a given hypothesis. But first we want to put that in context. So let's talk about hypothesis tests in general. Hypothesis tests are also called tests of significance. Now back in 4.1 and 4.1 learning outcome number 4 and 4.1 learning outcome number 5, we used probabilities to determine when sample results were significantly high or significantly low. Chapter 8 is just formalizing that. We're formalizing those concepts into a unified procedure called a formal hypothesis test that's used in many different fields, social science, science. This is used everywhere. It's a very powerful tool. Now, before we talk about significance, I want to review the basic procedure and the big picture for hypothesis testing again. We always start by writing our claim in symbolic form and using it to infer a null and alternative hypothesis. Hypothesis testing is about testing a claim. So someone's going to say something is true. They're going to say, I claim that this is true. And the question is, is it? And we're going to be able to determine whether evidence suggests the claim is true, or whether evidence suggests the claim is false, or whether evidence suggests that the claim might be true or that the claim might be false using a formal hypothesis test. So we always start there. Now, in order to do that, in order to determine whether sample evidence suggests that we should support or fail to support our claim, we want to identify or compute a sample statistic and the sample size n. Sometimes they'll give us enough information to compute the sample statistic and the sample size, and sometimes they will just state the sample statistic in the problem statement. So you can either identify it or you can compute it yourself. The sample size n is relevant because it's related to that sampling distribution that we're going to talk about in the next point. Now, after that, after you identify the sample statistic and the corresponding sample size n, we want to graph the sampling distribution of the sample statistic, assuming that the null hypothesis is true, and label the sample statistic on the graph. So we've got this graph. We know that the null hypothesis is, or we're assuming that the null hypothesis is true. So that typically is giving us the value of the mean of that sample statistic. So we're saying that the true population proportion is this value, or the true population mean is this value, or the true population standard deviation is this value. So we know the mean of that distribution. And then we're saying, okay, given that that's the mean of the sampling distribution, where is the sample statistic on this graph? Is it extremely high, or is it extremely low? Is it significantly high or significantly low? That's the question. If it's significantly high or significantly low, we're going to say, wow, that's pretty improbable. It's happening, but according to this assumption, that's very improbable. If something is happening in reality and it's very improbable, it might be the case that our assumptions are incorrect. So what we do in that case is we say, okay, if this thing is happening in reality and it's very unlikely to happen, let's reject the null hypothesis. So we're deciding whether or not to reject the null hypothesis on the basis of whether that sample statistic is significantly high or significantly low, given the significance level that we're going to choose, which we're going to talk about in a little bit. Now, associated with that sample statistic, usually we're talking about, let's just, for example, throw out a sample proportion. Sample proportions, the sampling distribution of sample proportions tend to be normally distributed. So what we would have there with our sampling distribution is a non-standard normal distribution, like we talked about in lesson 6.2 in chapter 6. Well, in order to determine whether that sample statistic is significantly high or significantly low, it'd be easier to do that if we moved from our non-standard normal distribution to a standard normal distribution, where we could look at the number of standard deviations above or below the mean. So we would convert that sample statistic into the corresponding test statistic. So that would be a z-score for proportions. For means, sample means, we're going to use the student t distribution. For sample standard deviation, they use the chi-squared distribution. We're going to talk about that briefly in lesson 8.1, but we're not going to cover hypothesis tests for standard deviation in this course. So we're going to skip that, but we will touch on it briefly in lesson 8.1. So you compute the test statistic that corresponds to that sample statistic. And that test statistic is just going to allow us to determine whether the sample statistic value that we obtained is significantly high or significantly low. You can do this in one of two ways. You can use the critical value method, which is using a value on that horizontal axis and comparing critical values on the horizontal axis to the value of your test statistic. Or you can use the p-value method, which is dealing with probabilities associated with the test statistic, which is associated with the original sample statistic. So whether we look at areas under the curve or values on that horizontal axis, we're going to come up with the same conclusion about the null hypothesis. Or if the probability is small enough for relative to a desired significance level, we will reject the null. So the probability being small would be related to the p-value method. Well, that probability will be small if the test statistic is extreme. There's going to be what's called the critical region, and you'd see that the value of the test statistic is in the critical region. So extreme values of test statistics are correspond to small probabilities. So option 1 and option 2 are going to give you the same conclusion about the null hypothesis. If that test statistic is an extreme value, extreme meaning statistically significant relative to a desired significance level, we're going to be able to make a decision about the null. If it is significantly high or low, we can throw out the null, reject the null. If it's not, we'll fail to reject the null. And then lastly, we want to state our conclusion in non-technical terms. So all that means is that we want to go back to that original claim, and we don't want to talk about p-values or critical values or z-scores or t-scores or chi-squared distributions. We don't even want to talk about null hypotheses or null and alternative hypotheses. What we want to do is we want to talk about the original claim. Are we able to say something about that claim? Are we able to say that evidence suggests that it's true, or evidence suggests that it's false, or something else, something similar to that? Evidence fails to suggest that it's false, or something like that. We'll see. It'll depend on the original claim, but we will always want to go back to that original claim and state our conclusion in non-technical terms. So if you've ever read an article in Psychology Today or like Scientific American or something like that, they might actually list critical values and p-values, but most of the time when journalists are summarizing results from the social sciences, they're stating it in a way that everyone can understand. We want to do the same thing for our readers. So again, the big picture is this. Our question to ourselves is, if this null hypothesis is true, is the value of the sample statistic significantly high or significantly low? Is this value unlikely to occur by chance? If it is unlikely to occur by chance, so it corresponds to a very low probability, it's like, this is very unlikely, and say, well, maybe our initial assumption is wrong. And our initial assumption was that the null hypothesis was true. So we would reject the null hypothesis. Now, if the sample statistic isn't extreme, or it could have easily occurred due to chance, given our assumption, well, then we can't say anything about the original assumption, actually. The sample as evidence is inconclusive, and all we can say is that it doesn't warrant rejection of that assumption. We can't say that the null hypothesis is true, but we don't have enough evidence to suggest that the null hypothesis is false. So here we would fail to reject the null hypothesis. Again, for our example from the last video, if we're looking at, say, a sampling distribution of sample proportions, and we're assuming that the population proportion is equal to 0.5, And then we get a sample statistic, a sample proportion of 0.59. The question to ourselves becomes, well, is that 0.59 likely to occur by chance or not? If it is likely to occur by chance, we say, well, maybe p equals 0.5 is correct. We can't be sure, but sample evidence does not suggest that we should throw out that possibility. But if p hat equals 0.59 is extreme, given that assumption, we might say, maybe our assumption is wrong. Okay, so we talked about all of this, and I don't know about you, but I am definitely one of those students who always says, well, what do you mean by that? In calculus, we talk about limits and we talk about things, as x gets infinitely close to c, f of x, y equals f of x gets infinitely close to L. We're talking about limits, or not infinitely close, arbitrarily close, or as x gets closer and closer to c, y equals f of x gets closer and closer to L. And if in my calculus class, we almost always say, like, I always ask, well, what do you mean by close? And then we talk about the epsilon delta definition of closeness. In statistics, the idea is about significance. We say, oh, well, that's significantly high. That's significantly low. You might say, well, what do you mean by significant? How high does it need to be significantly high? How low does it need to be significantly low? We're saying that it's different enough from what we expect, but what do we mean by enough? We've got to quantify that. And we quantify that using probabilities. Now, what we mean by significance is related to this value, the significance level alpha for a hypothesis test. This is quantifying what we mean by significantly high or significantly low. It's the probability value used as a cutoff for determining when sample evidence constitutes a significant evidence against the null hypothesis. This is the probability of mistakenly rejecting a null hypothesis when it's actually true. This is the same alpha value discussed in chapter 7 and associated with the critical values and area that we talked about back then. We've got critical values, we've got area in the tails, and that's associated with alpha. So alpha equals 0.05, alpha equals 0.01, and alpha equals 0.10 are typical. That's exactly what we would expect. Okay. So we're again asking this question. Now remember, whenever we draw this sampling distribution, this is only accurate assuming that the null hypothesis is true. We're saying, assuming that the null hypothesis is true, the mean is this. What can we say about that null hypothesis being true, given this value of p hat from our sample? Now, if p hat is significantly high or significantly low, we're going to reject the null hypothesis. We're going to say, gosh, that's very unlikely to occur by chance, but it's occurring, so let's reject the null hypothesis. But let's say that the probability of getting a p hat value that high or higher than that is 3%. 3% is not zero. I mean, it is still possible to have a p hat value that's that high or higher than that at 3%. So there is a chance that you could get that p hat value and the null hypothesis is actually true. So then we would be making a mistake. We'd say, this is very improbable, so our assumption must be wrong. But actually, it's just this improbable thing that's happening that, 3 out of 100 chance is actually occurring in real life. So if the sample statistic is significantly high or low, we're going to assume that our initial assumption is wrong and we reject the null hypothesis, but sometimes we're going to be wrong about that. The probability that we're wrong about that is called alpha. Now, if the sample statistic isn't extreme relative to this null hypothesis, like maybe if our p hat was, let's say, 0.51, say, well, that could easily happen due to chance. So then the sample evidence is inconclusive, so we can't say anything about the null. It might be that the null is not 0.5, but evidence doesn't suggest that it's not 0.5. So we're going to fail to reject the null in that case. But again, it's possible that we reject the null when we're just looking at a particularly unlikely value of p hat that just occurred due to chance, then we would be making a mistake. That leads us to type 1 and type 2 errors. So we're either going to reject the null if that value is significantly high or significantly low, or we're going to fail to reject the null if the value of p hat or x bar or the sample standard deviation is not significantly high or low, is sort of typical given that the null is true. So we're going to make one of those decisions. Now, type 1 error is the mistake of rejecting the null hypothesis when it's actually true. And that's just that alpha, that significance level alpha. That's the probability of a type 1 error. So this is the probability of rejecting the null when the null is true. So we're saying this thing is very unlikely to occur and it occurred, therefore reject the null. Well, maybe it's just unlikely to occur and it occurred, and we shouldn't have rejected the null. That would be a type 1 error. Now, type 2 error is making the mistake of failing to reject the null hypothesis when the null hypothesis is actually false. The symbol beta is used to represent the probability of this error. This is the probability of failing to reject the null. So saying evidence does not suggest that we should reject the null, but actually we should reject the null because it's false. So maybe we need more evidence in that case. That's type 2 error. So I love this graph. It can help you understand these ideas a little bit better. In this top row, we see the state of reality. So in reality, the null hypothesis is either true or false. So we've got this column represents the null being true, and this column represents the null being false. Now in this first column, this leftmost column, we see not what's actually true or false, but what evidence suggests is true or false. So maybe evidence suggests that the null hypothesis is false. So we've got an extreme value of the sample statistic and we reject the null. Or maybe evidence suggests that we shouldn't reject the null. We look at the sample statistic and it looks sort of typical given the null hypothesis. And so we can't say anything about the null. We say, well, this could easily happen due to chance, and we can't accept that it's true, but there's not enough evidence to say that it's not true. So we're going to fail to reject the null. Well, that leads to two possibilities or two possible ways of being right. And there's two possible ways of being wrong. So let's talk about rejecting the null hypothesis first. So let's say evidence suggests that the null hypothesis is false and the null hypothesis is actually false. That was a correct decision. Good for us. So we looked at the sample statistic. The sample statistic was extreme, and the sample statistic was extreme because the null hypothesis was actually false, and it was a good idea to throw out that null hypothesis. So we're good to go over there. Now, another way that we could be right is to fail to reject the null hypothesis when it's actually true. So that means sample evidence suggests that we shouldn't reject the null hypothesis. We don't have enough evidence to reject it. And that's a good thing because it's actually true. That's when we're in this case here. But it's possible that evidence might suggest that we reject that null hypothesis. The evidence might suggest that the null hypothesis is false when the reality is that the null hypothesis is true. That's a type 1 error associated with probability alpha. Now, the other way that we could be wrong is that we could fail to reject a false hypothesis. So evidence might suggest that, well, we can't really say anything about the null. The null might be right or it might be wrong, but the evidence does not give us enough, does not warrant rejecting the null. That might be the case. Well, at the same time, the null is actually false. So we might need more evidence. That is a type 2 error that's associated with this probability beta. Okay, so now I just wanted to give you a couple of hints associated with this. First, these descriptions of type 1 and type 2 error refer to the null hypothesis as being true or false. And sometimes it's difficult to keep track of these. So I'm going to give you a couple more examples before you go to the homework and try to keep track of these on your own. Type 1 error is rejecting a true null hypothesis. Type 2 error is rejecting a false null or failing to reject a false null hypothesis. But whenever you are talking about type 1 error or type 2 error, we don't want to use this idea of rejecting a true null and failing to reject a false null, because not everybody knows what a null hypothesis is. We always want to state our conclusion in terms of the original claim, the claim in the problem statement. What did we say at the very beginning? That's how we want to talk about our errors in terms of that claim. So here's an example. I actually got this from my friend James Slides, James Wiley at Tulsa Community College. He gave me his slides the first semester that I taught statistics, and they were wonderful, and I'm very grateful to James for helping me in that way. But he used this example, innocent until proven guilty, to talk about type 1 error and type 2 error. So here's the assumption. In our country, in our criminal justice system, we assume that someone is innocent until we prove that they are guilty. I mean, you could live in a different culture where we assume that someone's guilty until they're proven innocent. That's not the way we do things in the United States. We assume someone's innocent, and then we look for evidence of guilt. If there is sufficient evidence of guilt, we reject this idea that they're innocent. So we're rejecting the null hypothesis, and we call them guilty. We say that this person is found guilty. Now, if we are assuming innocence and then we go to court, we're talking about maybe criminal court, and then we fail to reject the null, so we look at the evidence. We might not be able to say, we can't prove that this person is innocent, but we can say the evidence is not enough to suggest guilt beyond a reasonable doubt, right? So that's failing to reject the null. Now, before we get to that, there are two ways that we can be right about this. So if the person is truly innocent, so we're in this column, the null hypothesis is true, and we fail to reject the null hypothesis. So the evidence does not suggest that the person is guilty. So we've got an innocent person, evidence does not suggest that they're guilty, so that person would be found not guilty. Unfortunately, you'll never be found innocent in our court system. You're either going to be found guilty or not guilty, but the innocent person is found not guilty, and that's good. That's better than being found incorrectly found guilty. Okay, so that's this right here. An innocent person is found not guilty. Or it might be the case that the person is actually guilty. So the null hypothesis is false. And then the null hypothesis is false, and we've got evidence to suggest guilt. So we reject the null. So if the person actually is guilty and the evidence suggests guilt, then we're rejecting that false null hypothesis. So we're rejecting the idea that that person is innocent because evidence suggests they're guilty and they're actually guilty. Guilty person is found guilty. That's a correct decision. Now, when we talk about error, type 1 error is the error of finding an innocent person to be guilty. So this is where the null hypothesis is true. The person is actually innocent, but for whatever reason, evidence suggests that this person is guilty. So the person looks guilty, even if they're not actually guilty. So this is where we're rejecting a true null hypothesis. We're rejecting the idea that the person is innocent when they're actually innocent. So that's an error. So an innocent person found guilty is type 1 error. Now, type 2 error is failing to reject a false null hypothesis. Now that's got a lot to it, failing to reject a false null. I mean, there's so many negatives there. Let's think about what this is. This is where a person is guilty. In reality, the person is actually guilty, which means that the null hypothesis that the person is innocent is false. But if the person is guilty and the evidence does not suggest that they're guilty, the then we would fail to reject the null. So we would fail to reject the idea that they're innocent, and this guilty person might be found not guilty. So we're making a mistake there, and the probability of that type of error is called beta. This is failing to reject a false null hypothesis. The fact that the person is guilty means the null hypothesis is false. The fact that we are finding that person not guilty is failing to reject the idea that they're innocent when they're actually guilty. So that's type 2 error. Now, in our country, we seek to minimize this type 1 error. So it's more important to us that we do not find innocent people guilty. It's more important to us to minimize this as opposed to minimizing this. Usually, my understanding is that as type 1 error, like type 1 error and type 2 error are such that you can minimize one, but it has an impact on the other one. So if we're minimizing type 1 error, we might have a larger type 2 error. Please correct me if I'm wrong about that. But the idea is it's more important to us that we don't find innocent people guilty than it is that we, find guilty people to be not guilty. So we sort of protect the innocent person here by minimizing type 1 error as much as possible, as opposed to trying to protect a guilty or prevent type 2 error from happening, which is where a guilty person is found to be not guilty. So type 2 error might happen more often if we're emphasizing this type 1 error, which is making sure that innocent people aren't found guilty. Okay. So I hope that helps you a little bit make sense of type 1 and type 2 error. Think about that some more. And remember, our null hypothesis here is that we're assuming that that person is innocent. And then we're saying, okay, does evidence suggest that they're guilty or not? If evidence suggests that they're guilty, we're rejecting the idea of innocence. If evidence suggests that they're not guilty, we're failing to reject the idea of innocence because evidence is not enough to prove guilt. And when I say prove guilt, I just mean provide evidence of guilt, sufficient evidence of guilt. But in either case, whether evidence suggests guilt or not, or non-guilt, whether evidence suggests guilt or evidence is not sufficient to warrant us to label that person guilty. We could be wrong. We could be wrong in this way, or we could be wrong in this way. So here's an example that is more like the problems that you'll see in your homework. It says, consider the claim that a medical procedure designed to increase the likelihood of having a baby girl is effective. So we've got this procedure. It's supposed to increase the probability of having a girl. So the probability of having a girl is greater than 0.5. So if it's increasing the likelihood that of a baby girl, and we're saying typically chances are 50-50. You're going to have a girl or you're going to have a boy. So the probability is actually equal to 0.5. Or the probability and proportion we're using here interchangeably. If we're saying that it's increasing the probability of having a girl, we're saying that when you use this procedure, your probability is actually greater than 0.5. It says, given the following null and alternative hypotheses, write statements describing type 1 error and type 2 error. Actually, we could come up with the null and alternative hypotheses ourselves. So the claim is that P is greater than 0.5. If that's not true, P would be less than or equal to 0.5. The one that does not contain the condition of equality is the original claim. So that's our alternative hypothesis. So P is greater than 0.5. And the null always has an equals sign. So we just change that greater than sign to an equals sign to get the null. Okay, so now we want to describe type 1 error and type 2 error. Type 1 error is rejecting a false null hypothesis. Or I'm sorry, rejecting a true null hypothesis. Wow, tired. So the following is a type 1 error. So the null hypothesis is that the probability of having a girl, even after using this treatment, is 50-50. So P is equal to 0.5. But if P is actually equal to 0.5, and sample evidence suggests that P might not be equal to 0.5, but the sample evidence is wrong. P actually is equal to 0.5. That's type 1 error. So that's just what I just said. In reality, the probability of having a girl is still 0.5, but the evidence suggests that the probability of having a girl using this treatment is 0.5, or is greater than 0.5. Now, in terms of the original claim, we would say, in reality, the probability of having a girl is still 0.5 when using this treatment. So that means that in reality, the treatment has no effect. But for some reason, our sample evidence suggests that the procedure works. So we're wrong. The procedure doesn't work, but evidence suggests that it does work. Now, type 2 error is the mistake of failing to reject a null hypothesis when it's false. So this is when evidence does not warrant rejecting the null hypothesis, but we should reject the null hypothesis because it's actually false. So in reality, the probability of having a girl when using this treatment is greater than 0.5, but evidence suggests that, well, from the data that we have, from the sample proportion that we have, we cannot warrant rejection of the idea that the true probability of having a girl when using this procedure is 0.5. Or in other words, here we are concluding that we have no evidence that the medical procedure has an effect. There is no evidence from our study because the value of p hat that we got was not significantly different from p equals 0.5. It was sort of typical. But if that data suggests that p might be equal to 0.5, but actually this procedure is effective, that's type 2 error. So I hope that helps you make sense of type 1 and type 2 error and understand that idea of significance. Again, the significance level is the probability of rejecting a false null hypothesis, or probability of rejecting a true null hypothesis. I'm sorry, I'm misstating that. But basically, it's the idea that we get a value of a sample statistic that's significantly high, and we say that because it's significantly high, the probability associated with it is low, so we should reject the null. Like, that's the way we come up with our conclusions every time based on that rare event rule that we talked about earlier. But if it's associated with a small probability, maybe it's actually happening, but the reality is that the null is true. So that's type 1 error, and type 1 error is equal to our significance level alpha. So I will see you in the next video to talk about test statistics. That is the last thing that we need to talk about before we can actually do a hypothesis test, putting together the ideas that we talked about with learning outcome number 1 and learning outcome number 2, and then in learning outcome number 3. So I'll see you in the next video.